Hello, and welcome back to Teaching Systems in the Classroom, Session 2. My name is Jeff Ryan, and I'm the Regional Science Coordinator here at Olympic ESD. Hopefully by now you've worked your way through Session 1, which is titled, What is a System? And this is a follow-up to that. If you haven't, that's okay. You can certainly still go right into this one, and it's in this session that going to provide some sort of concrete tools for thinking about how you would teach systems in your classroom. And before we start, let's go ahead and overview what you're going to need for this. First, you're going to need a systems thinking framework, which you can find on this web page, linked below the session number 2 documents. Samples of completed systems thinking frameworks, energy transfer diagram introductions, energy transfer diagram template, the Washington State Science Standards, the 2009, of course, and a notebook, paper, and pen. So, why don't we go ahead and leap into this. Now, first thing I'd like to do is a little bit of a elicitation question, kind of like what we did in the first section, what is a system? But this one is related to our state science measurement of student progress, as we call it, the MSP assessment. And what I'd like you to do is take your piece of paper from your notebook and a pen or a pencil, and if you're working with colleagues, I'd like you to do this together. Make a pie graph like you see here on this diagram right here in 4 quadrants like that, and then what I'd like you to do is fill in the pie graph based on what percentage you think systems, inquiry, application, life science, earth science, and physical science makes up of the total MSP, like in any given like MSP assessment that's given to, say, the 5th or the 8th or the 10th grade. Actually, in the 10th grade, we have biology in a course, so why don't we just say 5th or 8th? What percentage of this pie graph do you think is made up of each of these? So go ahead and pause the video now and complete that, and when you're finished, if you have a conversation, if we're working with more than one person, when you're finished, you can go ahead and continue the video. Okay, welcome back, and I'd like to go through. So when we left, the question was how much of the MSP is systems, inquiry, application, life science, earth science, and physical science. And this gets a little bit at the question of, well, why teach systems thinking here? And here's a good reason. This is a test map, generic test map from the Science Measurement of Student Progress Assessment here in Washington State. And you can see systems represents roughly 20% of the exam every year, or the assessment every year. And in addition to inquiry, you can see is 30, application 20, and then you can see earth, life, and physical 30%. Now you can see that these three together, these cross-cutting ELers as we call them, systems, inquiry, and application, you can see that this works up to be over 50% of the exam, which surprises a lot of teachers because a lot of times we end up focused over here on the content without a lot of thought given to the cross-cutting ELers. And unless you're working with an instructional material that really supports you in understanding these cross-cutting ELers, then it often is a challenge for teachers to be able to really embed these into their instruction and their day-to-day instruction. So I'll note that the content is also present. Let's take systems for instance. You're probably all aware that the state MSP, Science MSP assessment has system scenarios in it, and those system scenarios are around a life science system or a physical science system or an earth science. So there's a content context for these system scenarios So it's not like they're not assessed in some way within these system scenarios. But anyway, that's the breakdown for the test map and why it's important to not only because we want students, as I mentioned earlier in the other section, to be systems thinkers, but we would also see that it is definitely a part of the state assessment. It's definitely what we are asking students to do in our standards. Okay, so this is a systems thinking framework, which I asked you to download earlier, and I want to acknowledge where this framework was developed. This systems thinking framework was developed by ESD, the folks down at ESD 112 in Vancouver, Washington, Southwest Washington. Specifically, Mark Watron, who is no longer the regional science coordinator down there. It is now Gloria Ferguson, but they have a wonderful cadre of teacher leaders and have done a lot of work in supporting the rest of us here in the state, and I wanted to acknowledge them. So I'll explain a little bit of how to use a systems thinking framework, because you're going to use one in a minute. But in a real general sense here, you can see around the outside here is kind of this first rectangle goes, why use systems thinking? Well, we've gone into that extensively already, and I just showed you that systems is 20% of the measurement of student progress, and this is actually outdated here. This is no longer the HSPE, but it is now the biology end of course. But systems is also high in the biology end of course as well. So which systems will we focus on? Physical systems, earth and space, living systems. Here's the big idea I referenced earlier. And then you can see, and we can see the grade levels here broken down. Systems, this is what we call systems speak at the different grade levels, and this is K3. And as I mentioned earlier, here you're talking parts and whole with your students, or functions of parts. You want to predict if you take away a part of a system or something, how is that going to change the overall function of that system? When we get up into 4th and 5th grade, the system speak that we'd be using with our students is about subsystems and systems, inputs and outputs, functions and predictions of that, and then so on up into 6th and 8th through 8th grade. You can see that it builds upon the 4th and 5th grade, so inputs and outputs, boundaries and flow, open and closed systems, and then up in 9th and 12th grade, we have feedback, negative feedback, and equilibrium. So this first sheet here just shows an overview of the systems thinking framework. But let me show you the next slide here. This is what you're going to be working with, because this is actually a scaffold, if you will, for you to use to help think about how you're going to be talking with your students in your classroom about the systems that you are studying in your science instructional materials. And so it's basically for identifying and describing relevant system in your science kits or your science textbook or whatever you're using here. And you can see this center circle here. This is for where you identify the system that you're focusing on. So this could be anything. It could be a tree, it could be a rubber band car, it could be a lever and pulley system. There's lots of options for what goes in the center box here. And then after you identify that system there, then basically what you do is you fill in these boxes around the outside here to consider that system in more detail and to help you communicate that system in the components, the different parts of that system, to use the system speak, if you will, with your students. So this is really a planning tool for a teacher, although I have heard teachers say that they use this framework, thinking framework, with their students. But believe you me, I've watched some teachers work through these together, and they are nice thinking tools. They really helps to be able to work your way through one. So before we start, and I ask you to do one, so let me just go over. So basically, you're going to identify a system, something that you teach in your instructional materials. You're going to complete this thinking framework, and with the idea that it's helping you consider instruction and assessment, because we'll be using this framework here actually to think about assessment in just a minute. But here's an example of one that you have in the packet that you printed out earlier. So this is actually, as I mentioned, this is a rubber band car system. And then you can see over here they start to identify the subsystems within this. So wheel and axle. The wheel and axle transfer energy from the rubber band to the surface to move the car. So this actually also talks about energy transfer within the system. And this is a physical system here. And as I mentioned earlier, the reason why we're studying systems here, or we're using it, because a system identifies a boundary from which we can then, as science educators, as scientists, as students, think about the energy transfer, transformation, and the flow of matter through that particular system as well. Okay, so that's kind of in. All right, so here, as I mentioned, here are the boundaries, and this talks about the boundaries of this rubber band car system. The surface is the boundary, the person is another boundary. And then here the rubber band energy, the elastic potential energy will be transferred to the wheel and axle subsystem. And then here the input, the energy is the hand, the person provides the energy that is stored and stretched in the rubber band, that stored elastic energy. Energy conservation, most of the energy results in motion. Some of the energy is transformed into heat through friction on the surface of the table as the car moves forward. And then motion output. The car moves as a result of the energy that is put into the system. So this rubber band car system is actually from a FOSS kit, Models and Designs. And one of the things that strikes me immediately is that, as a teacher teaching this particular kit, it's really about design, the design process and redesigning, and it's a great kit to help to meet the application standard. Yet what this brings forward here is the potential to talk about energy transfers, the potential to talk about the rubber band car as a system, things like that, which are sorely lacking in the instructional materials. They do not provide teachers with the support. But going through this sort of process then would help you, the instructor, articulate that so that you're better prepared to actually teach and think about that system with your students. So now's the time that I'd like you to pause the video and create your own, using that thinking framework, your own, identify your own system, and then work through that framework planning sheet. And we'll see you in a few minutes. Hello and welcome back. By now, hopefully you have worked your way through the systems thinking framework, and now what I'd like to do here is, and if you have any, if you want some samples, I'm not sure if I mentioned this in the previous clip there, if you'd like some samples of already filled out systems thinking frameworks, there's that one that was in the handout on the rubber band car, and then I'm going to upload a couple more to the website here. So we're going to transition a little bit now here to considering energy transfers in your system. And so really the purpose of this session here is going to be to kind of review a little bit about energy transfers, give you a format, an energy flow diagram that you may or may not be familiar with, as a way to both for you to consider energy transfer in the system that you identified earlier, and also for you to be able to communicate to your students depending on the age of them. This is probably most appropriate starting at about 4th or 5th grade. But give your students a way to start to communicate to you and to their classmates about the energy transfers that they see in the systems that we're studying. So here is an example of an energy transfer diagram here that I was describing. So in this simple diagram, if you're not familiar here, usually starts with a source, an energy source. An energy transfer happens here, that's what the arrow represents, and then there's some sort of energy receiver. Remember, energy moves through all different kinds of systems. It's not created and it's not destroyed, but it's transferred and transformed into different forms. In this case, they have like something, an example like the sun or a battery, and as it is transferred, it decreases in energy, like depending on what form it is. So whatever the original, like if it's a battery, it has stored chemical energy, so it decreases in stored chemical energy. It's transferred over, and let's say it's a light bulb that's receiving the energy. So the light bulb would increase in, and this would be light energy, I guess, and also there's a release of thermal or heat energy from the light bulb in a circuit system. So this is the general idea of how this goes. Now you can connect these, but let me go ahead and show you a worked up one from our earlier example of a rubber band car system. So this shows just one step here in energy transfer through the rubber band car system. Starting with the arm, your arm, if you're pulling that rubber band car across the floor, and if you're basically using your muscle energy, your chemical energy, to mechanically transfer energy to the receiver, which is the rubber band car in this case, and specifically you're going to get an increase in stored elastic energy. Okay, so again, the source is your arm, decrease in the chemical energy, the stored chemical energy in your arm, mechanical energy transfer over to the rubber band car, which is going to increase the rubber band, specifically an increase in stored elastic potential energy. And this now, one of the challenges in this kind of diagramming is often to decide not so much the source and the receiver, because you can easily identify that in the system, but it's more about, well, what kind of energy are we talking about, and it's and also what kind of a transfer are we talking about. So there's a couple of different resources here to help you think about that. Number one, there's a handout that I mentioned at the beginning of this, which is the energy transfer diagram, basically sheet, and it looks like this here. And it has kind of an explanatory paragraph at the beginning, along with, which might help you, the different kinds of energy. It describes energy, just kind of gives you a real brief overview. This is a real kind of a general overview for folks that might need it. In addition to that, let's move on one more slide. We have a handout that looks like this. Now this is an incredibly crazy looking diagram here, but let me just kind of give you a general overview. So this is all the different interaction types. It talks about contact, gravitational, magnetic, electrical charge, electric circuits, heat, convection, conduction, all these different interactions. And you can see these different types: applied, elastic, or friction. And then if you look down here, so contact requires objects that push or pull on each other, and that is, as I was describing in that last one, mechanical energy transfer. Objects near each other, also mechanical energy. It's gravitational. Magnetic, when you bring a magnet near an object and it pulls it in, it's also mechanical energy transfer. So this just gives you a sense of what kind of transfers here for these different types of interactions. And here's the example. So this is kind of a, this here helps you kind of clarify, if we go back, what kinds of transfers we have to help you in understanding this diagram a little better. So let me go forward. So I provide this for you. This resource here, I first encountered this at Western Washington University in the North Cascades Lumbus Science Partnership project that I was involved in for a few years, and it helped. And we the teachers that sorry, let me go back. We, the teachers, had to do a lot of this energy transfer diagramming in the different modules we're in, whatever the systems we were studying. Very early on, we did a lot of this to get a sense, and used a document like this to help us, depending on what kind of interaction we were seeing, and then that gave us the different kinds of transfers that might be going on. So this is available as a handout as well for you as you work your way through. All right, so now is the time for you to go back to the system that you have articulated already on that systems thinking framework, and consider the energy transfer through that system, transfer and transformation through that system. There is a template that is also available on this website here to allow you to illustrate that energy transfer in the system. And the purpose of this really is, whether or not it's useful for you as a teacher, but you can also communicate to the students using these energy transfer diagrams, again, depending on the age of your students, but I'd say from about 4th grade on up, 4th, 5th grade, students can start to identify the types of energy, talk about energy transfers through systems. And again, the reason we use and we focus on systems in science is because it helps us identify boundaries, and there, from those boundaries, then we can talk about the inputs and the outputs into that system, and specifically how energy transfers and transforms within that system. So go ahead and pause this and take a moment to do that. Okay, welcome back, and hope you found that exercise useful. Diagramming the energy transfers in that system that you identified. We are going to move forward into the reflection now, and so with your notebook, just take a moment, if you will, to consider what we've done in this session here and answer this prompt. How will you use the systems thinking framework and the energy transfer diagrams to inform your classroom instruction for the rest of this year, hopefully, or whenever you have an opportunity next to talk about systems in your science classroom?